Here in this video, we take one thing for granted that pressure of a gas molecule is equal to 1 by 3 density VRMS square. We have derived this equation in the previous video, just in the previous video. In case if you are having any doubt, please refer to the previous video of this chapter and this playlist. I'm not going to derive that. That's a lengthy derivation. Taking that for granted, we can further see how can we work with that further. Say, let us multiply this equation with 2 and divide with 2 so that you can get another format. 2 by 3 multiplied and of course 1 by 2 divided with 2 rho VRMS square. VRMS square. Now this is equal to 2 by 3 of what is remaining is half rho VRMS square. So it is like half mv square where that's a representation of a kinetic energy, but what is here missing is density equal to mass by volume is there, right? So it's kinetic energy per unit volume. This is what are you talking about is kinetic energy per unit volume. Of course, you will be getting it for per gram because you are calculating each of this for one molecule of the gas, right? You can express it in terms of say R equal to something like a Boltzmann constant by number of the molecules. So kinetic energy can be expressed in the other format, like in the place of 3 by 2 RT, I can write 3 by 2 K by N in the place of R and T. So that will become something like 3 by 2 KT per mole. So we can write 3 by 2 RT per gram depending on a requirement, or 3 by 2 KT per mole where K is called as Boltzmann's constant. Coming back to our equation, we can say total pressure is equal to 2 by 3 of kinetic energy of the gas molecule per volume per gram, as I have already mentioned to you. Now you can further modify this equation. You can write in a format like taking this equation further into consideration, same equation. We got an equation as pressure equal to 1 by 3 rho VRMS square. I will simply call VRMS as something like C for the sake of simplicity. Now density can be written like total mass by total volume whole square. That is P. Get the V to this side. PV becomes 1 by 3 mc square. But we know PV is also equal to, as per ideal gas equation, per 1 mole, PV is equal to RT. So I can write this equation as RT is equal to 1 by 3 mc square. So if I multiply this with 3 by 2, on both sides, 3 by 2 RT equal to 3 by 2 of 1 by 3 mc square. This 3 and this 3 can be cancelled. That is half mc square. So what we can say here is 3 by 2 RT is equal to half of mc square. What is that? This is average kinetic energy of the gas molecule per gram. This is so what we can conclude here is average kinetic energy of gas molecule per gram is 3 by 2 RT. If you want to write it per mole, it will become, instead of 3 by 2 RT, as I have explained earlier, it becomes 3 by 2 KT. Both are same, only for the sake of understanding, we can write it in different formats. Taking that basics into consideration, we can further write, yeah, I'll just continue this discussion so that we can go ahead and further, as we have proved 3 by 2 RT equal to 3 by 2 RT, sorry, this is equal to half M VRMS square. I'm writing this from here equation, from this equation. Half m VRMS square 3 by 2 kT equal to then 3 by 2 RT equal to, yeah, I have already proved that 3 by 2 RT equal to here. Yeah, I'm just taking this equation for consideration. From here, I can cancel this 2 and 2. I can write then VRMS square equal to what we can write? Square 3RT by M. It implies VRMS and is under square root of 3RT by M. From this, we can say VRMS is directly proportional to square root of, be careful, this is absolute temperature, not a temperature in centigrade, but it is a temperature in Kelvin. Be careful about that, right? So that's all about the first part that we are talking about RMS velocity. Next, I would like to talk about what is an absolute zero is, right? So I will just scroll down a little so that I can write comfortably. Right. So what is an absolute zero that we are talking about, right? The B part, absolute zero temperature. So from the derivation that we have made, VRMS is directly proportional to square root of temperature, that whatever we have got. At absolute zero, at t equal to 0, VRMS also becomes 0. Means what? The gas molecule simply stops moving. They are in a kind of a still state. That's no more like in a gas state itself, actually, because gas molecules actually cannot stay as in a kind of a still state. That means that's the temperature at which any gas gets converted into other formats, right? So, for a definition sake, we can say the temperature at which RMS velocity of a gas molecules becomes 0 could be called as a absolute zero temperature, right? So, for an ideal gas, the value of that absolute zero temperature is minus 273 degrees centigrade. That is taken as a reference, and a Kelvin scale or absolute scale is defined. That's all about absolute zero. Now, I would like to talk about the one more last part that was being asked to find out. That is, how do we relate these two velocities, like velocity, RMS velocity? We have already just now discussed that RMS velocity equal to root of 3RT by M. This is here. We have derived this relation. We know velocity of the sound. We have discussed it in earlier using Newton's Laplace correction. That's value is root of gamma RT divided by M. This looks very close to each other, but they're different. Be careful. There is a gamma here, which is the ratio of the temperatures. So if you try to find the ratio of these two gases, that is VRMS by velocity of the sound, what will be remaining is everything gets cancelled, that is 3 by gamma. This gamma depends on the nature of the gas. For monoatomic, gamma is something like 5 by 3 for diatomic, 7 by 5 for monoatomic, that is 8 by 6 star, that is 4 by 3. So be careful about that, right? So RMS velocity, first thing that I want you to understand is this RMS velocity, though initially you got it in terms of a pressure like 1 by 3 pressure VRMS square, this VRMS velocity is independent of pressure. Rather, it depends on temperature, right? That I want you to understand. Why I do say that is, if you remember the equation that what we got, VRMS in terms of pressure, you got a density also in the other side, right? So when pressure increases, density equal to mass by volume, no, volume decreases and density also increases. And their ratio always remains constant. Therefore, pressure cannot impact the RMS velocity. Rather, absolute temperature can definitely impact the RMS velocity of a gas molecule. That's it for the day. It's a long post. I want you to understand and see back all this video once again if required so that you can get a better clarity. Thank you for watching.